Thank you, everyone. Excited today to talk about delivering high-quality generative video. Today we'll be sort of exploring two frontiers, how we're thinking about natural video infrastructure and how that's evolving with generative video content, right? How can we evolve both natural and generative content as it comes into streams? We'll talk about two frontiers here, thinking about the research and technical breakthroughs, and also a fascinating case study with a generative video app that has grown to over 1 million users in 3 days, and thinking about this. So I'll pass it on to Sophie to talk more.
So we are the founders of Sima Labs, which is a startup working on AI-based video tooling. So this talk is going to be structured in 3 parts. First, we're going to talk about how codecs can be optimized for GenAI video. Then we're going to discuss the CDN infrastructure, and then we'll talk about how we can efficiently deliver interactive experiences with generative content. So let's first talk about codecs. So I want to first take a look at what a standard encoder-decoder structure looks like in GenAI video architectures. So when I talk about encoders and decoders here, I'm not referring to standard codecs. I'm talking about the neural networks which are present in diffusion models and other related video models. So here we have a input tensor going into the encoder, getting compressed down into a very small latent representation, then getting decoded into a standard video. So what you'll notice here is that this encoder-decoder structure inherently has a very powerful compressive ability in the latents that it creates. So when we are transmitting GenAI video, instead of taking the reconstructed output and recompressing that with a standard codec, we can directly transmit the latents to client-side devices on which we deploy decoders to reconstruct the intended video. So by utilizing latents for transmission, we not only spend less computation in the entire pipeline, but we also get a much smaller data representation. So you can kind of think of this as transmitting the intent behind the video generation instead of the pixels themselves. In other words, it is a highly compressed, abstract version of the semantics of the video. An important property of these latent tensors is that they are very well suited for bandwidth adaptation. And the reason for this is that these GenAI models inherently understand what is important for the video content that they are creating. And so they can much more intelligently remove information when we are operating under low bandwidth conditions. So I want to talk more about that in a second. But first, let me show you what is possible with latent codecs. So here we have the same 2 images, which are compressed with 3 different codecs. The first is H265, which achieves a 21 PSNR score at 0.86 bits per pixel. VP9 achieves a slightly better 26 PSNR score at 0.57 bits per pixel. But the latent codec achieves a 45 PSNR score, which is almost a perfect reconstruction at 0.06 bits per pixel. That is an order of magnitude of difference in the bitrate. So now let's talk more about the technical details of how exactly we can implement bandwidth and compute adaptations for GenAI codecs. In a standard video, when we need to reduce the bitrate, we typically either apply stronger quantization or we reduce the spatial resolution of the video. Both of these techniques create spatial artifacts which are visually displeasing. So with GenAI codecs, we can remove the information much more intelligently. For instance, a model can understand that the background of a video is much less important than the foreground. So in the background, you can remove unimportant objects, use simpler colors, create more redundant textures. You can even represent background information in lower int4 or int8 precisions, while the foreground is kept in full detail and full precision. We should also remember that these latent representations are inherently matrices. So there are various properties of these matrices that we can exploit to efficiently remove information. For instance, if we want to get rid of unimportant objects or details, we can drop low energy channels in the latent tensor. If we want to significantly reduce the number of elements in the matrix, we can apply matrix factorization techniques. And remember that the decoder understands how to create visually coherent video on its own. So even if there's information missing in the latent tensors that we are sending to decoders, they can still create a high-quality video by filling in the gaps. So of course, there's another side to this, which is that we may not only be limited in bandwidth, but we can also be limited in client-side compute. So there's a plethora of research which has gone into figuring out how we can run big ML models in limited compute environments. And all of that applies here. For instance, in a diffusion decoder, we typically have a series of denoising steps which need to be taken to achieve a final video. So we can apply early exit schedulers to significantly reduce the number of steps that need to be taken and therefore cut down the time of computation. We can also apply distillation techniques to reduce the total number of parameters in the decoder significantly while still being able to create a high-quality video. Okay, so now we've covered how codecs can be optimized for GenAI video. Let's also discuss our existing CDN infrastructure. For natural video, we typically have this one-to-many paradigm, where there's one content creator and hundreds or thousands or millions of viewers who are all looking at the same piece of content. But GenAI streaming is not always one-to-many. There are interactive, personalized, and ephemeral video experiences that we want to deliver, which break existing CDN caching procedures. Personalized content places a huge load on the origin server, while the rest of the CDN essentially becomes a pass-through network as each video is only being played back once. So the solution to this is to shift towards a distributed origin and edge computing focused approach. Instead of having one data center where we cluster all of our GPUs, the GPUs should be geographically distributed and brought closer to client-side devices. So by pushing compute to the edge, we now allow for adaptations such as, if your phone cannot run a full decoder, we can offload the heavy steps of that computation upstream to an edge GPU which sits very close to your location. And now the video can remain in its latent form for the vast majority of the distance that it needs to traverse before it gets decoded for your phone. So with this re-architecting, the CDN essentially becomes more of an active generation and delivery network rather than the standard tree of caches. So now I'll pass it to Rushaan to talk more about how we can efficiently deliver interactive experiences for GenAI video.
Thank you. Interactive experiences are one of the most engaging use cases for consumers. And when we think about this here at Sima Labs, one fascinating case study has come up recently, which was a video company called Descartes.ai. Their first product, Oasis, reached 1 million users in 3 days, faster than the growth of ChatGPT to 1 million. What makes this incredible is the experience of generating video games in real time. How can you do this with low latency and think about it as input as keystrokes and output as pixels generated on the screen? What makes this even more fascinating is their most recent video-to-video product. Think about camera feed input, and output is a generation talking back to you, almost like generative FaceTime. We currently do FaceTime a lot in our present day. Think about this as an input camera feed, and output is a generation model talking back to you, right? And so as these use cases become one-to-one in a generative video experience, we rethink what the architecture can be. And part of this is the technical challenges around prompt-to-pixel latency. This is a fascinating metric because prompt-to-pixel needs to be really, really fast to have a beautiful consumer experience. It has to be under 200 milliseconds. And to unlock this, we have to think about what does it look like to do model partitioning. Model partitioning is thinking about breaking apart the components of inference for these video models and delivering that in parallel to run fast. As well as we think about speculative execution. How do we think about the likely next prompt? Remember, we're talking to this model in real time. So how do you think about what is the next prompt the user is going to ask? And you have to prepare for that in speculative execution. A big part of personalization is thinking about one-to-one, right? And so what makes the user-specific custom options to be able to think about this every time a user has their context? And part of this is video context, right? We think about LLMs and how context is super important. In this case, we're talking about user-specific video context. And so one of the things I'm most fascinated about here is scaling laws. when we talk about video interactions and people using them, these models are getting better. These video models talking back are becoming more personalized and only getting better as you use them more. And that's what's most exciting. As you scale up data, you scale up the compute, and you also scale up the way these interactions happen and how user sessions become more exciting and more personalized. So with that, I want to talk about making this real in a production system. Part of what's most exciting here is how do you do this with edge points of presence, right? When you have to keep a user session active and making sure that it actually works in both encoders and decoders and in the architecture, you have to make sure that when you pause the video in natural video and you reopen that same video in another application, you expect it to just play back. I pause it in one device and I reopen another device, it just has to work. And it works today for natural video. For generative video, the video context is super long. We're talking about a generative FaceTime. If you pause it on one device and reopen another device, this is actually a GenAI model that has to keep all the context and restart the conversation. So how do you do that efficiently? And as Sophie talked about, how do you do this with generative latents, right? Generative latents being transmitted over the wire. And so part of this to us here is we think about client-side frame caching and what does this look like optimized? How do you do this whole pipeline from encoding to decoding to also distributing this? But part of building any great production system is thinking about fallbacks. And how do you make sure you have your main generative stream, but you also want to make sure you have your standard codec proxies ready, whether that's H264, AV1, and the coming great work with AV2. And as we think about this as an industry, how do we think about both the production mainstream with generative latents and also your standard codecs that need to be there to keep a fallback for these incredible consumer experiences? So with that, I want to take us to 3 key takeaways for today. Part of what we started here is we built out an amazing infrastructure as a community here, thinking about video infrastructure for natural video. How do we optimize that also with the inclusion of generative video? And what does that look like? Second of all, we really think that as you have a surge in content, we don't want to have a surge in costs for generative content as it integrates into natural, whether that's in streams, VOD content, live content, whatever that looks like. And lastly, I've been really fascinated by how in personalized video, you have these amazing high ARPU use cases, whether that's personalized ads. I was thinking about the other day, I was talking to someone in a company that is generating videos. Instead of having a classical car go down in your regular ad, what if you actually generate the ad with your family inside the ad, right? And now the interactiveness of that becomes a lot more appealing, and these ads are returning a lot more from ROI perspective. And so how do we optimize these to think about quality, think about delivery, and really see this overall? And lastly, I want to leave us with a keyword. Sima Labs is really thinking about what does generative delivery look like, and how do we evolve that as a community? So happy to take any questions afterwards. I know we're going into a break. I want to give a big thanks to the Momento team as well for organizing this amazing conference. And with that, thank you so much.
Thank you.